Hello, my name is Guolong. In this video, I would like to introduce you FLACK, a tool to automatically localize faults in alloy models. This is the alloy analyzer interface. I would like to use an address book model to show you how FLACK can help the alloy developers locate faults in their models. In this address book model, we define three types: address, name, and book. And the book has two fields: entry, which is the set of names, and listed, which maps the entry to a set of names or addresses. We also define a function lookup that finds all the names and addresses associated to a given name. Then we have facts to put some constraints to the model. A name entry maps to at most one name or address. All names reachable from any name entry in the book are themselves entries, and the name entry should be a cyclic. Then we have another effect to restrict the number of values we want to use for each type. For example, we only want one book, one address, and two names. Finally, we have an assertion to assert that for all the name entries of a book, there has to be some address set associated with it. Then we have this check command to ask alloy to find some counterexamples for this assertion. And alloy actually find these simple counterexamples for which validates the assertion in which the name one of the book is not associated with any address. The alloy analyzer, the alloy developer will then need to go back to the model and check each line and find that, oh, I misused long here. If I replace this long with some, this would fix the problem. For this model, all this process seems to be simple. However, when the alloy model becomes much larger and complicated, this becomes much more hard for human being to localize faults. For example, in this surgical robots model, which models the surgical robots with arms, and we specify an assertion that the robots need to produce some feedback if the arm goes out the limit of the arm. And when we check the command, we got the following counterexample, in which the counterexample is much more complicated, and it would be hard to understand what's going on with this counterexample. And the alloy analyzer will then go back to this model and check all these expressions to find the buggy expression. To help the developer, we introduce FLACK, which takes in the counterexamples and use a PMax set solver to generate instance that satisfies the property specified in the assertion, and using some different analyses to find the minimal difference between the counterexamples and the satisfying instance. And the FLACK would then use this information to slice the alloy model and calculate a score for all the suspicious expressions. Next, I'd like to show you how we can use FLACK in practice. You can invoke in the root directory of FLACK, you can use this command to invoke FLACK. You can use the F option to specify the location of the model you want to check, and use the M option to specify the number of pairs of counterexamples and satisfying instance you want to use. For example, for the address book example, FLACK actually outputs the ranked list looks like this, in which we can see the buggy expression was ranked first. FLACK would also output some statistics about the execution, like the total analyzed time, the number of different relations and different values FLACK found, and the sliced out and total AST node. For the robots example, FLACK actually outputs this ranked list, which actually greatly helps the alloy developer to find the error. So thank you for your time, and you can download FLACK using the following GitHub link.